In this video, I'm going to explore the inputs that we enter into solvers, and then the outputs that are generated by the solvers as the solution. We'll start with the inputs. Now, the inputs, I've talked about this in previous videos, but to reiterate here, the inputs of a solve are simply the parameters that we enter into the software to define the state of the game or model the situation that we plan to study. We'll vary those inputs to test our assumptions and ultimately develop insights that we can translate into heuristics, and we can translate into strategy, and ultimately translate into things that we can use in our execution at the tables. Now, I've listed out here on this slide the various inputs that we can control within the solvers, and that starts with the stack to pot ratio. Now, the solver is going to require us to enter effective stacks and pot size separately, but actually it's the ratio of these two values that actually influence solver outputs. The second thing the solver is going to require us to enter are community cards. Now, whether we're starting with the flop, the turn, the river, we need to enter those community cards that are known on the board at the point of the game tree that we plan to solve. It's somewhat less relevant if we're looking at pre-flop solves, which we'll talk about at some point later. But even then, we do have to enter some type of board conditions that we plan to examine. Bet sizing, or the game tree construction, is going to be examined at each decision point, and that ultimately forms the construction of our overall complete tree. We'll get into this in a little bit more detail, but those selections are usually generally limited due to the processing power and or the memory that we have within our particular machines that are running the solvers. Ranges, which are the combination of hands that make up each player's range, and it includes the overall set of all of the possible hands that could be played by either player. These can be pure or they can be weighted down to the combination level. But it's important to note that the hands that we select are the only ones that will be included within the calculations, and they're the only ones that will actually impact the solver output. Strategic decisions and or node locking. So while strategic decisions and the frequencies at which we take certain actions with different combinations are generally an output, those can also be fixed as an input through node locking at one or multiple nodes. We'll get into this in a lot of detail in later modules, but this is extremely valuable when we're actually demonstrating and developing exploitative strategies. And then finally, there are some additional tree building functionality that many solvers have baked in to account for things like rake or ICM and other game situations that can impact the overall expectation value, and they can be accounted for in solver calculations. So let's go through each one of these individually so we can kind of get a sense of what those inputs mean and some of the options that we have for those various inputs. So we'll start with stack to pot ratio. For each of these views, I'm going to show some screenshots of the two primary solvers that we're going to be using at the start of this course, GTO Plus and PioSolver. There's plenty of other solvers out there on the market. I will be expanding on this course in the future and continue to add different demonstrations and different videos that might be based off of additional solvers. But we'll start with just kind of the two major ones that are on the market here in the US, GTO Plus and PioSolver. Now, as I mentioned, the stack to pot ratio is the most important portion here, but ultimately the effective stacks and the pot size are required as inputs to build the tree. And I've highlighted here on GTO Plus and PioSolver examples of where you would enter that information. You can use any unit of measure here. So you could use currency. So use this in dollars. You can enter this in blinds. You can enter this in tournament chips. The actual unit doesn't necessarily matter, but you must remain consistent throughout the tree. So if you enter your effective stacks as dollars and then enter your starting pot as chips, if those values don't equal one another, you're going to end up with some weird outputs and the calculations aren't going to make very much sense to you. And as I mentioned here before, the ratio of those two values is really all that matters here. So it's the stack to pot ratio that matters, not necessarily the effective stacks or the pot size. So if I set up a solution with a $100 pot and a $1,000 effective stacks, that's a 10-to-1 SPR. That's going to yield the same exact output if the rest of the tree is the same, and I'm looking at a solution with a $5 pot and $50 effective stacks. So again, the ratio of the two, the stack to pot ratio, is all that matters for this calculation. Moving on to community cards. So I've highlighted now here on these screenshots here where you would enter the community cards in both GTO Plus and PioSolver. Community cards are required for post-flop solutions. So pre-flop simulations are computed using all or a subset of boards, but for post-flop solutions, we actually have to start with a board, whether that's a flop situation where we're entering a flop, a turn situation where we enter the 4 cards, the flop and then the 1 card of the turn, or a river situation where we enter all 5 cards. But those community cards are required as a starting point for our analysis. Now, solutions can be generated really from starting from any street. So we can start with the flop, we can start with a turn, we can start with a river, but we need to have the community cards that also align to that specific street that we're starting at. Specific suits don't necessarily matter as much, but there are exceptions depending on individual starting ranges. But the most important thing here is that patterns must remain consistent. A Jack 10-5 rainbow board will model the same as any Jack 10-5 rainbow board. There's 24 different ways for a rainbow board to be configured with all of the different 4 suits. And you can use any one of those 24 different ways, and you're going to get the same exact solution, provided that you don't have any differentiation in your preflop ranges with regards to specific suits. But an ace 2-4 two-tone board where the ace and the 2 are the same suit will not model the same as an ace 2-4 two-tone board where the 2 and the 4 are the same suit. So there has to be some form of symmetry, but within those various boards if you're going to substitute out one or another. For reference, there are 22,100 unique flops, and of those 22,100 unique flops, 1,755 of them are actually unique from a strategic perspective. So you can boil down that 22,100 flops to 1,755 flops based on a concept called suit isomorphism. The next thing is bet sizing, and bet sizing options just really describe the basic parameters of the game tree, and it ultimately generates our initial configuration of the game tree. As we've covered in previous videos, the game tree is really the construct of the game in which we're actually solving. When we enter these bet sizing options, it's going to ultimately build out a game tree where we have various bets and raise options on flops, on turns, on rivers. And by entering some of these options within the boxes that you see here on the screen, it helps us do so in a simplified manner so that we don't actually have to physically draw each of the individual nodes throughout the entire game tree. Now, each tool, whether it's PioSolver or GTO Plus or other tools like Simple Postflop or things like that, they're all going to have somewhat different syntaxes, but all of which are generally flexible enough to allow for some detailed customization, which would include things like multiple bet sizes, situational betting and raising. So sometimes you may want to force hands to do certain actions like check. Sometimes you may want to have certain bet sizes for probes and certain bet sizes for donks, whereas if you're continuing as the aggressor from the previous street, you want different bet sizes. And a lot of tools give you various flexibility, which we'll explore in some later videos. And as I mentioned here, adding complexity to the game tree on earlier streets will generally have a greater effect of the size of the tree, and also the memory and the CPU power that's needed to find a solution than doing so on later streets. So it's a lot easier to add a lot of different bet size options on rivers and turn than it is on flops. Because by doing so on flops, those additional parts of the game tree that you're adding are going to continue through to turns and rivers, and you're going to end up with very, very massive trees by just adding 1 or 2 bet sizes additional on flops. And again, we'll cover a lot of that in later videos too. The next input we're going to look at is ranges, and ranges for each player must be entered to complete the simulation. And what we do is we enter the ranges at which each player arrives at that particular street that we're starting at. So even if we're entering with a preflop scenario. Generally, if we're using a preflop simulation, we start with ranges of all of the possible hands, and the solver works down to an output that generates the ranges with which we should actually be playing and the ranges with which we should actually be folding. For post-flop scenarios, we generally start with a more condensed versions of the overall ranges because some of those hands that we would originally put into a preflop simulation have already been folded preflop. So we'll start with a flop specific range, or if we move forward to turns or rivers, we'll start with ranges that are even more condensed than that. Now, ranges are going to have the most significant impact on the output as compared to the other inputs. So higher accuracy in estimating our ranges is going to yield a much more accurate output and a much more accurate game tree. What we can do here is we can actually weight hand combinations to allow for the discounting of certain hands based on actions. It also allows us to hedge for scenarios where we might have less certainty, and we'll talk a lot about that in Module 3, where we talk about building game trees and entering different ranges. The next thing that we have here is strategic decisions or node locking. Node locking is the act of selecting and locking specific strategic decisions within the game tree. And this is not required to run any simulation. This is an optional component of things. But node locking is utilized to implement very specific tests in your poker studies, such as maybe modeling various player profiles and ultimately trying to identify maximum exploitative strategies. The overwhelming majority of the value that you're going to get out of solvers is going to come from the experiments that you run while node locking. Node locking is an area where we're going to talk about a lot within this course, and we're going to go through a lot of different examples of how you can node lock different ranges to yield answers that you may not be able to get otherwise by looking at equilibrium solutions. Finally, additional tree building functionality. Most solvers have added some scenario-specific features that can help customize the tree construction process. Things like rake or ICM, they're going to impact the overall EV calculations. Using rake as an example, the casino takes money out of the pot for rake. So our overall pot size at the end of the hand is actually going to be different than it would be if there were no rake taken out of the pot. And that's going to impact EV calculations, which is ultimately going to impact the different strategic decisions that we can take with each individual hand within our range. The solvers have allowed for some additional tree building functionality that lets us account for things like rake, that lets us account for things like ICM in tournament scenarios, so that we can build more accurate trees, and that helps us ultimately build a more realistic model of play that which can hopefully yield a more actionable output. Now, those are really all of the inputs that we can enter within a solver. And in module number 3, we're going to go through those inputs in a lot more detail as we actually go through and talk about how to build and construct game trees and some of the decisions that we might make and why we would make those decisions in the process of building a game tree. Now I'd like to move on to the outputs that the solver generates. So after entering all of those inputs and running the solver is going to generate a set of outputs for us to interpret. And I'll introduce some of them on this slide and go through some of them in a little bit more detail on the subsequent slides. Now, solver outputs are the data points that are generated as a result of those various inputs or those constraints that are entered within our tree construction. All of the outputs that are generated are very specific to the node at which we are examining. So I highlight that because it's very, very important. So in other words, there's a unique output that's generated for every single node in the game tree. And because of this, it's important to be very clear about the perspective at which you are viewing the hand. What I mean by this is that the expectation value of each player, the equity of each player, other metrics will be very specific to each individual node, and as you work through the game tree, those values will differ. So you need to be very specific at the individual node at which you're looking at things for each individual output. I've mentioned a couple of the outputs already. So the first output that the solver generates is equity. And equity is an output to some degree, but it's really only dependent on range interactions. What equity represents is the frequency at which the specified player would win the pot if no more action would happen through the rest of the hand. So it's not dependent on strategic decisions. It's not dependent on future action. It's only dependent on the two ranges that are present at that given node and how those two ranges interact with one another and the frequency at which either one of those ranges would win the pot if the hand was checked down from there to the river. Expectation value. Expectation value is king in solvers. It's the primary measure of success in poker, and it represents the amount that we would expect to win or lose through gameplay. Now, EV is a function of many things. It's a function of things like position, equity differentials, range composition, but ultimately, expectation value is going to be the primary metric at which solvers are trying to optimize. And it's also going to be the primary metric that leads us to the decisions at which we take throughout the course of game trees. Now, there are derived metrics that some solvers generate, some solvers don't. We can actually sometimes also even take some of the raw data out of solvers to derive some of these metrics ourselves. So things like EV percentage, which we'll define as the share of the pot that we win on average, or EQR, which is short for equity realization, which is a percentage-based metric that is native to PioSolver, not necessarily native to GTO+, but it measures how much more EV that we would win or lose than we would expect to win given the equity of our ranges. We get a lot of raw data out of solvers, and sometimes we can derive some additional metrics that can help generate some additional insight into the way we might want to play a hand or a scenario. And then finally, the strategic action frequencies. I have that as an input, and I also have that as an output. What solvers will do as they're trying to optimize for expectation value is that they're going to vary the set of strategic actions, so things like raising or calling or folding or betting within a range to ultimately reach a final state of equilibrium. And these specific values of the strategic actions are an output of the solution. And the strategic action frequencies are kind of interesting in the sense that they can be an input, it can be fixed through node locking, or they can be an output when we're not necessarily fixing them. They get varied as a part of the solution. And let's go through each of these in a little bit more detail. So we'll start with equity. As I mentioned here, equity are dependent on the range interactions, and they represent the frequency at which the specified player would win the pot if there were no more action throughout the rest of the hand. The value of equities will vary at each node of the game tree, as I mentioned, and they should be viewed as a snapshot at that particular point of reference. So if you're looking at an equity at the beginning of a flop calculation, that is going to be the equity at the beginning of that street. But after one player checks or after one player bets, by default, they are going to narrow a little bit of their range, assuming that they're not taking 100% of their hands and putting them into one of those different actions. So if they check with 50% of their range and bet with 50% of their range, the next node of the game tree will see different equities, because now at the next node of the game tree, the solver is going to look at that condensed range that only bets, or that condensed range that only checks against the opponent's range. It's important, again, to look at things at that particular node or at that particular point of reference, because equities, again, are only going to be looking at the two ranges at that point in time against one another. So, and that's what I mentioned right here. Equities are only dependent on the ranges of both players at the game node. It's not dependent or affected by gameplay or future action. Now, values of 50% are neutral. So if both players have 50% equity, it means that they're both entitled to half of the pot or the same amount of the pot if the hands were checked down to the river. As that distance from 50% grows, aggressive actions within ranges become much more present. And we'll see examples of that, particularly as we look through solver outputs in Module 4 and beyond. The next metric is expectation value. Again, as I mentioned, it's the most important metric that we'll use to measure the success of any particular range or hand. And it represents the amount of units, which is consistent with the input that we chose, expected to win in the hand from that particular node. Like equity, it takes into account only the information that's available at that particular node. Unlike equity, though, it's dependent on our strategic decisions, the other players' responses, and future action. Remember that raise-shove game. Our expectation is going to be dependent on what other players do, right? So from the small blind's perspective there, the small blind is going to take certain actions by raising, and the big blind could then either shove or fold. In that scenario there, the small blind's expectation there is going to be very dependent on how frequently the big blind shoves and how frequently the big blind folds. EV is anchored to the size of the pot at that particular point in the game tree. So also, if you remember from the game trees that we discussed earlier, the EVs of both players, if we add them together, they're going to equal the pot size at that particular point in the game tree. So it's unlikely that we actually see values larger than the pot size, which would mean that one player has a massively positive expectation value and the other player actually has a negative expectation value. It doesn't happen often, but it does happen sometimes, particularly at the individual combo level, or as we get down closer to the river where equities run further apart, and some players may have close to or even 100% equity. The next one is strategic action frequency. So usually most solver analysis starts with looking at the strategic decisions at which the solver generates. It's the first thing that we generally look at. If you're looking at the screenshots there to the right, we like to look at the portion of our overall range that bets, the portion of our overall range that checks, etc. That generally is the thing that most people like to do, is understanding, well, what should my particular hand or what should a portion of my particular hand do at any given time with the information at which we have. Given the inputs, each hand combination within a range is going to be slotted into a set of strategic actions that are available. So, raising, betting, calling, or folding. And that represents the equilibrium output of the constructed game tree within that certain margin of error that we delineate at the beginning of the solve. Combinations can be mixed within calculations unless we did something to force them to be pure within the software to determine a solution. So even down to that individual combination level, if I take a look at the screenshot on the slide there, the top one, we can see that the ace-jack suited combinations, they're not purely betting. A portion of them are betting. So ace-jack of spades is betting 87.6% of the time in that example. Ace-jack of hearts is betting 82.3% of the time. Ace-jack of diamonds is betting 82.0% of the time. And ace-jack of clubs is betting 82.5% of the time. But it's also checking a portion of the time as well, too. And that's the beauty of solvers, is that solvers can work down to a very precise solution by mixing individual combinations to determine a solution. Now, there does exist a margin of error, so different solvers might have different solutions for the same game tree, which can be confusing to some, particularly when we get to the more granular hand combination level. So generally what you'll see is if you look at solutions for different solvers, at the macro level, for an overall frequency perspective, you're going to see frequencies stay fairly close to one another for a solution. But once you start getting down to the micro level, the composition of that overall range might differ from solver to solver. That's because there is a margin of error that we bake into things. And there might be other strategies, and sometimes many different strategies, to a given game tree that will look somewhat different, but it'll perform similarly from an overall perspective as it relates to EV. And remember, solvers don't care about the range composition. They don't care about anything else. They're only caring about trying to optimize that expectation value metric. And the final thing we're going to look at is the additional derived metrics. It's sometimes helpful to derive these additional metrics to analyze a scenario. Expectation value, equity, they're excellent measures, but it's sometimes better to manipulate them, particularly in some data analyses, or to extrapolate them to find additional data that can help explain the scenario better or inform different strategies that we might take. So I have a few of these here, and I've covered a couple of them already, but I'll introduce a few derived metrics. But it's important to note that this is not a complete list. Others can be created, others can be used depending on the analysis. But the first metric that I'll go through is the EV percentage, which measures the relative percent of the pot that the player's EV is worth. It's calculated by dividing the EV by the pot size. What this does is it actually normalizes the metric for us. So EV is a raw number, and as a raw number, it's difficult sometimes to compare between different boards, between different scenarios, because the values are going to be different. The pot sizes are going to be different in different scenarios. But by converting it to a percent, we normalize that metric, and we can compare it to different scenarios much more easily. We can also compare things to equity, which helps lead us to the next metric of equity realization, or EQR, which measures how much more EV that we would win or lose than we would expect to given the equity of our ranges. Now, equity realization, or EQR, is calculated by dividing the EV percentage by the equity. Values of over 100% here means that we will over-realize our equity. And values of under 100% mean that we will under-realize our equity. And what we'll see here when looking through the outputs are that equity realization are going to correlate heavily with the aggressive actions that a certain player can and will take in solver outputs. Values of over 100%, and especially as they move further and further away from 100% and get higher and higher, they're going to correlate with more aggressive actions for an overall range. Whereas values under 100%, or as it moves lower and lower down to 90% or even lower, it's going to correlate with more passive actions or more of a realization-based strategy. So equity realization, though, is very important, and it helps us take a look at or get some insights into how different ranges may perform from a strategic action perspective. The other thing that we can look at here, and I like to look at this a lot, is the amount of nut combos in one's range. And the way I define this is it measures how many hand combinations that the advantaged player has in their range that's better than anything in an opponent's range. We can think of a scenario here where we have an under the gun open and they're flatted by the big blind, and the board is ace king 2 rainbow. Well, we know that it's very unlikely for the big blind to be flatting with hands like aces, with hands like ace king, and with hands like kings. Right away, we know that there are a certain number of combos that will definitely be in an under the gun opening range, but it's not going to necessarily be in a big blind defend range. And that can be useful to help us determine the aggressive actions, or how big and how frequently we can be betting as the advantaged player. It also can be useful to look at this as a percentage of the entire range. Rather than just looking at the raw number of nut combos in one range, it's more important actually to have a higher nut combo percentage. It's better to have 10 nut combos in a range of 100 hands than having 10 nut combos in a range of 300 hands, because the 100 hand range is more dense or more weighted towards having nut combinations in that player's range. But we'll cover all of these in a lot more detail when we get into Module 4 and we go into solver outputs. So now that we've gone through and introduced the inputs and outputs, in the next video, we're gonna actually take a look at both of them together and see how different inputs and varying those inputs are going to affect outputs, and understanding the relationship of those two sets of variables. So I'll see you in the next video.